In this example problem, we have a uniformly charged rod of length L. So this is the length L from here to here. And let's say it has total charge Q on it that's distributed uniformly. What we want to do in this problem is find the electric potential at the location of this green X here. So let's say that the distance from the green X to the end of this rod is Y, and that, let's say this is perpendicular right here. So this line here is perpendicular to the rod. We want to find the electric potential here. Now, this thing is not a point charge, so we can't just blindly use the formula for the electric potential due to a point charge to find the electric potential here. Instead, we need to handle this as a continuous charge distribution. So we can modify the formula for the electric potential due to a point charge as follows. That is, the contribution to the electric potential of a infinitesimal chunk of charge dq is just the electric constant k times dq times divided by the distance from dq to the location where we're interested in knowing the electric potential. Note that k is just shorthand for something that's often written this way. K is 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. Okay, so let's apply this. To use this expression, which we're going to eventually put in an integral, what we need to do is find some prototypical dq along this charge distribution, represent the distance from there, straight line distance from there to the field point with our r, and then set up a function that we can integrate so we can get all the contributions to the electric field. Of course, depending on where you are on this charged rod, there'll be a longer or different r, a different separation from the thing producing the electric potential to the location where we want to know the electric potential. So setting that up as an integrable function is the trick. Alright, so let's get started. So let's look at some little bitty chunk of charge, infinitesimal chunk of charge, dq. We can write that dq, that little chunk of charge, as the charge per unit length, lambda, times the little differential length, dl. Now, what's lambda? In the case of a uniformly charged rod where the total charge Q is spread uniformly, that is evenly along the length, the charge per unit length will just be the charge divided by the length. Next, we need to identify our R, which is just this, the separation of the chunk of charge producing the electric potential to the location we want to know the electric potential. Now we need to figure out how to put this R in terms of something we can integrate. Now this Y isn't changing, but this thing here is changing. That's basically what we're integrating. We're looking, adding up, taking all the contributions for if this little chunk of charge is here, or here, or here, or here, or here. We want all those contributions. So let's parameterize or find a thing for represent this length right here. So let's call this X. We might as well. Of course, now we've got to make some modifications to what we've written before. I had dq is lambda dl, where dl was some differential length. Now, if I'm representing this thing here by x, then some increment of that, some little infinitesimal of that, would now be a dx. So that's x is our variable of integration. My dq will now become lambda dx. Okay, so we're almost done. We now need to express this r in terms of our variable of integration and of other stuff that's not going to change. We can do that using a Pythagorean theorem. R squared will be x squared plus y squared in this picture, so we can put that in there. So now we're ready to put it all together. I'm going to leave the k as it is because that contains all this stuff. The dq now becomes lambda dx. The r is replaced by this, and we have this expression. Now, keep in mind that the electric potential is a scalar. So what we have here is the contribution to the electric potential at this point from this little bitty bit of charge. All we got to do to get the the electric potential at this point from everything is just to sum up all these contributions. That means doing an integral. So integrating both sides, we get so we get this integral. Notice here, let's just look at the units. KQ over L, that has units of electric potential. This is dimensionless, right? dx, that has units of length. X squared plus y squared, but take the square root, that has units of length as well. So there are no units in here when all is said and done. All the units are here. Units are correct. Now let's actually do the integral. I'm going to take the short way. I'm going to just use Wolfram alpha. So here's how you put it into Wolfram alpha. Here's what it gives me. And so we finally, since we have the result for this integral, we can plug that in here and we can get our solution. And again, we note that this has the right units. These are units of electric potential. This is dimensionless. The inverse hyperbolic sine of the dimensionless quantity will be dimensionless. So we've got the right units. And note that this y could have been any value. Not just this particular value, but it could have been further up here or a little bit less. So we actually have the electric potential as a function of y, provided that y is along this direction, perpendicular to the line of charge. Now, let's do some reality checking with our result. Now, we've already checked the units and made sure that they work out, but what we can do is examine the situation in the case where y is much larger than L. Because if that's the situation, the picture would look something like this. So, if this is L and this is y, what it looks like is that at some point here, it looks like all the charge is more or less at some point. And that becomes more and more a good approximation as this y gets larger and larger and larger compared to this length L. So what we should have ultimately is that for y much, much larger than L, we should have a situation where the electric potential as a function of y looks like the electric potential a distance y from a point charge q. So that's what this should approximate to in the event that y is much, much larger than L. So let's see if that works out. To do that, we can expand this function in terms of a Taylor series and then approximate that series or truncate it in the limit where this is a really small number, much less than 1. So let's see how that plays out. Using Wolfram alpha to expand the inverse hyperbolic sine of x, we get this Taylor series expansion. Expanded about x equals 0. Now look at this. Look at this. For x much, much less than 1, well, x cubed and x to the 5th, those are going to be even smaller compared to x. So for x much, much less than 1, this term, all that will be negligible compared to the x. And so in that limit, the inverse hyperbolic sine of x is approximately just x. Now, here, x is just some, argument for this function. In our actual problem, instead of x, we have L over absolute value y. And this is just the limit we're interested in. This quantity will be much, much less than 1 when y is much, much, much greater than L. So let's plug in this approximation into our formula here and see what we get. When we do that, these L's cancel and we get that in this limiting case where y is much, much, much larger than L, which can also be written this way, we get that the electric potential is approximately equal to K times the charge Q divided by the distance y from the charge. And this is the electric potential formula due to a point charge. So our limiting case checks out.